Yeah, so thanks, Tony, and also thanks the organizers for the invitation. So I'll talk about some properties of hard rods, some results on hard rods that we have recently obtained. So these are based on these two works. One is on archive, another will come soon on archive. And these are done in collaboration with several people. Sahil and Jitendra, graduate students at ICTS. Devarsi was a postdoc at ICTS, and Abhishek Manas is here. Harvard from Munich University, and David Hughes and Veer from Princeton University. Okay, so for generic many particle systems, which are not integrable, such systems from generic initial conditions eventually thermalized to Gibbs state, characterized by few conservational laws like mass, momentum, and energy. And such systems typically have good dynamical properties such as chaos, mixing, ergodicity. And evolution of these systems on macroscopic scale can be described by hydrodynamic equations with Navier-Stokes Fourier dissipation terms. And these are the hydrodynamic equations that we have seen many times. Okay. But the situation for integrable systems is different because they have extensive number of conservation laws, local conservation laws, and they fail to thermalize to Gibbs state. And it is believed that such systems with local conservation law thermalize to generalized Gibbs state upon coarse graining, and the corresponding hydrodynamics is written in terms of the quasi-particle densities and which obey generalized hydrodynamics. And I'll tell you about these hydrodynamics. So what is the generalized Gibbs ensemble? So this is the simple table that I made. So by comparing the non-integrable case and the integrable case. So non-integrable systems, given the Hamiltonian, you typically have a few conserved quantities, for example, number, energy, momentum. And in this case, the Gibbs state that you write is by maximizing the states corresponding to these values of the conserved quantities, you get this kind of Gibbs state, which is characterized by these three conservation laws. If you follow the same procedure for integral systems where you have extensive number of conserved quantities and maximizing the entry maximization gives you a generalization of that Gibbs state. So here you basically have all the conserved quantities with corresponding chemical potentials. Okay, so this is a slide I took from Benjamin's lecture note, which nicely describes the generalization. So for in non-integral case, you have finite number of conservation laws, and for integrable case, the generalization is that you have many number of conservation laws. And in this case, the stationary state, which is a homogeneous state, can be described by Gibbs ensemble. Here, it's generalized Gibbs ensemble. And if you have inhomogeneous state that evolves here, according to this hydrodynamic equations, and these hydrodynamic equations are actually obtained using locally this Gibbs state. And for this case, you also have hydrodynamic equations for all these conserved quantities, and the currents are obtained using this local generalized Gibbs state. So this is the generalization for integrable systems. And so these are some examples of classical particle systems that are integrable Toda model. And so then this is this one is hard rods. Then you have other models like Calogero-Moser and other models also. Not only particle models, we can also have spin models. So in this talk, I'll talk about hard rods, in which so basically you have collection of extended objects in one dimension. Each of them have mass 1, and interaction is that they cannot come closer than a distance a, and on collision they just exchange their momenta. This is the dynamics on a line. And this Hamiltonian has many conserved quantities. basically all moments of the momenta. Here I am calling velocity because mass is 1. All these are conserved quantities in this case. So in this talk, I have two parts. In the first part, I'll talk about this hard dot system on a line, and this is an integrable system, and I'll talk about the hydrodynamic equations for such system. And the other, in the second part, I'll try to talk about some results on if we try to trap them in some confining potential and what happens. Okay, so first part. So what is the hydrodynamics for hard rods when the rod length is non-zero? Okay, so for integrable systems, the hydrodynamics are written in terms of quasi-particles. So because multi-particle scatterings can be decomposed into well-separated two-particle scattering, as a result, you can have particles which can actually, for most of the times, follow some particular specified momenta, and you can think of quasi-particles. So quasi-particle is basically a tracer attached to real particles, and that changes from one particle to another particle in such a way that it follows more or less a given momentum. So these are some pictures that I took from Benjamin's lecture note. So this is what Toda system, where you have two particles. Let's say they start with some momenta and before scattering, long before scattering, and then after scattering they come out, but they come out with the same set of momenta, and they exchange as if this particle is basically, you can think of this as a quasi-particle having momentum P1. This is a quasi-particle having momentum P2. And this is easy to understand from hard rods. So these hard rods comes and they collide and they exchange momenta. And then this rod now goes with this momenta, and this rod goes with the momenta of the black rod. So if you follow a rod with a given momenta, that's a quasi-particle. Okay. So hydrodynamics for integrable systems written in terms of the densities, phase space densities of these quasi-particles, in terms of like what you write phase space density of single particle in particle systems. Here you have to write phase space density of the quasi-particles, and the hydrodynamics looks like this. It's like a kind of a single particle level type equation, but here you have some effective velocity. Okay, so I'll come to that in more detail. But ideally, you would like to write equations like for the conserved quantities, and there are infinite of them if it is in the thermodynamic limit, like density and the current. But it is convenient to write this in terms of this phase space densities, and you can actually see that if you have this, you can actually get these equations. So the densities are obtained as integrals of this phase space density, and the currents are obtained as like the flow of this conserved quantities integrated over the phase space distribution. Okay, so this is how you can write down, and in this sense, this is the generalized hydrodynamics. It generalizes the hydrodynamics of the non-integrable systems where you have few conserved quantities.
Sorry, what's the F?
I'll come to that. Okay, so for rods, hard rods, label exchange rods are quasi-particles. So whenever they collide, you just exchange the labels, and that becomes quasi-particles. And so you want to write down hydrodynamics for the phase space density of these quasi-particles. So before going into that, let's consider the case when A is 0, like point particles. So when point particles, two hard point particles, they collide, they just deflect off each other, and they exchange their velocities, right? So this one was going with velocity v1, and now it gets reflected and moves with velocity v1. It's like effectively. So if you exchange the labels, then they becomes effectively non-interacting particles at each collision, right? So, and then it is easy to write down, see, because you want to write down the single point distribution of the single particle in phase space. And if you use this non-interacting picture, it's basically just the Liouville equation. This knot represents the phase space density of hard point particles. Okay, so you just have velocity, and this is the Liouville equation for point particles, right? For hard rods, this equation just gets modified by an effective velocity. This velocity here for the point particle will be replaced by an effective velocity. Why? You see that when there for point particle, they exchange their velocity the collision happened at a point, exactly at this point, and then after that, this red particle starts moving there. But for here, this collision happens over a region, and after that, this black particle becomes red particle. And as if there was an extra displacement at the collision. If this red particle didn't see the black particle, it would have come here. If they are not interacting, it would have come here. Yes.
There is no, so this is the, okay, the rods aren't moving, right? So
This is in one dimension. Yeah. It would have come here, but because of the collision, there is an extra displacement. And you see that over time, if you follow a quasi-particle, that is a rod with a given momenta, fixed momenta, so this actually changes from one rod to another rod. So this is the position of the quasi, this is the trajectory of the quasi-particle. If this particle did not interact with other rods, it would have come here. Okay, but because of the interaction, it is coming here. And so there is an extra displacement, right? If it had come here, I would have written the Liouville equation as for the point particle. But because there is an extra displacement per unit time, there will be a change in the velocity, and that is incorporated here. Okay, and that gives you the effective velocity. So you can actually, I have some heuristic argument. So it's basically the let's say in dt time, what is the change of the displacement? So the particle would have, if it is not interacting, it would have moved by v delta t times. But because of these many particles that have collided with the particle, it made these many jumps in delta t time, and you divide it by delta t. And that is, so the current will be this times the density of the center of rods. And that's how you get the current in this form. So V effective times the distribution of the point particles, which you can write in terms of, you absorb this here, and so yeah, I use the same notation. I should not have used the same notation, but this is how we can see that the effective velocity gets changed. Okay, so
rho is always less than 1/8.
Yes, less than 1/8. And such quasi-particle motion can also be seen for other integral models. So these are trajectories of Toda particles, and you can see that this is the actual particle it is moving, but you can identify a particle with a given moment, and this is actually the quasi-particle. And you see that if this particle did not interact, it would have come here, but instead it came here, and there is an extra displacement, and that is incorporated by this effective velocity. Okay, and which you can see also here, that if it did not interact, it would have come here, but because of the interaction, it came here. So there is an extra displacement, and that is characterized, given the Hamiltonian, that is characterized by a phase shift. So phase shift is the properties of the Hamiltonian of the interaction. Okay, so for yes, so in general, you can write down a kind of an integral equation for the effective velocity, and you can simply interpret this. This is basically the rate at which the particles. This is the relative velocity. This is the rate at which these particles are coming per unit time, and the change in the displacement is this. So that's how this is the change in the velocity. Okay. So for hard rods, this quantity, this is called the phase shift. It is A, and you can do this. You can get the effective velocity as this. So this is the hydrodynamics for hard rods, and I should emphasize that this is the Euler scale hydrodynamics. But people have also computed the Navier-Stokes terms for this, and this is the explicit expression of the Navier-Stokes term, which was obtained by several people. For example, Benjamin and Herbert obtained it from Green-Kuo formula, and Boldirgini and Sohab computed it using some mathematically rigorous procedure, and then Benjamin and others, they have also conjectured such similar Navier-Stokes terms for other integrable models also. Okay, so I have these terms, and what do I want to do? So I want to verify, first of all, the solutions of this equation from microscopic dynamics, and I aim to study the evolution of non-equilibrium initial state and see if they approach generalized Gibbs state. And also in this evolution, I want to understand the effect of the dissipation term. So for that, what we do is basically compare the solution of the GHD equation with the same obtained from microscopic dynamics, and these are kind of typical trajectories of the hard rods. This is on a ring, this is on a box, and this to compute the solution of the GSD equations, as well as to perform the microscopic simulation, it turns out that this one particular transformation to point particle configuration is very useful. So this transformation is the following. Given any configuration of hard rods, let's say, you can construct a configuration of the point particle configuration by basically you just remove all the inaccessible space between any two particles. And this is the transformation, and the velocities remain the same. By doing this thing, your box size also becomes shorter, and you have a configuration of the point particles. And if you simulate this and then find the configuration at time t, and then again transform back, you should get back the configuration, final configuration of the hard rods. In fact, this transformation was actually used first time by Lebois, Parkas, and Sykes long back. So these are some demonstrations. So this is basically let's say initial configuration, hard rod configuration. This is point particle configuration, and you can independently simulate them. And these are the trajectories in the point particle. These are the trajectories of the hard rods. And after I find these trajectories, I can do the transformation, and I should get back this trajectories. And that's what you can see, that you can, by using this transformation, you can get these trajectories from these trajectories. This is a comparison. And I use the same transformation in the hydrodynamic equation also. And in the hydrodynamic equation, this transformation is written as this. It's the same thing. It's basically here. What was the transformation? The transformation is the point particle plus the number of particles below position I, because these particles are ordered. So below ith particle, there are I particles, but there is a factor half because there is a half distance from the wall. So it just basically you just shift it by I times A for each ith particle from point particle. Primes are point particle configuration. Similarly, here also you have there is a point particle hat X prime, and you add A times the number of point particles till X prime, and that will give you a hard rod at position X. So using this transformation, you can actually write down transformation between F and F naught. F naught is the phase space density of point particles, and this is phase space density of hard rods. And this is the transformation that you can figure out. And under this transformation, you can see that this Euler hard rod equations, which has this V effective, it becomes point particle hard rod. So you just have V. But only thing is that X has to be X prime. So everything is in X prime. So now you can solve this equation very easily. This is very simple equation. And this is just basically just whatever the configuration, you translate it with some velocity, initial configuration. So you can solve that equation, and then once you get the final solution, you transform it back and get the solution of this equation. So this is the same idea that we use in the microscopic simulation. Yeah.
Finite system, then you have boundary conditions.
Yeah, boundary is also shift. Yeah, in box and ring, things work out nicely. Okay, so as I said, we investigate the possible approach to GG, and which means that we would like to check if the system reaches time stationary homogeneous state at late time. Which means that if you start from such an inhomogeneous state, this is the density profile. The last time it should go to an homogeneous state, and the velocity profile should remain unchanged. Not remain unchanged. Initially, whatever the velocity distribution was, it should be the velocity distribution always like this, because the velocities do not mix here. Okay, and we should see what is the effect of Navier-Stokes term. So that means if there is a spreading, first of all, because of the this dispersive velocity term in the Euler HD, there will be broadening. But on top of that, we would want to see if there is a spreading because of the Navier-Stokes term. So that is what we want to see. So, and for that, we consider three different initial conditions. So this is the first initial condition in which we have two. So first, you uniformly fill the box with rods, but you put the density profile, velocity distribution inhomogeneously. The velocities of all these particles in the left half have velocity 1, whereas the velocities here are distributed in Maxwell distribution. So basically, initially the phase space distribution has two components. One is the special rods, which are initially at the left half, and I call these particles as background rods because they will basically become background at large time. So here the velocity distribution is Maxwell, and the full density is uniform. And if you ask what is how does the density profile evolve? And so this is how it evolves. This is so first I should say that even at late time, at any time, we should have these two components for this case because velocities do not mix. So you always have a special component for the special rods with velocity 1 and background rods. So I can look at the densities of these two components separately. So these special rods are initially in the left half, and the background particles are in the right half, and they evolve like this. And this is the time time increases in this way. So first it goes into these rods actually goes inside these rods, and these rods also enter into the region of the special rods, and that's how they enter. But their velocities do not mix. Okay, so here the dashed lines are simulation, and the solid lines are from solutions of Euler GSD, and we see very nice agreement. However, if you look closely near the SOC, you see there is some disagreement, and these disagreements are coming from Navier-Stokes terms. So if you look at this closely near the shock, then you see that at a small time there is a spreading, and the spreading is increasing with time. And this spreading, you have a square root t scaling. If you scale by square root t, all these curves actually collapse onto each other. Okay, so that means they spread near the shock as square root t. And it's not
Okay, so now the Stokes terms, what's the origin of them is from the initial conditions among the spread of
yes,
velocity condition.
yes.
So if you start with a more narrow distribution, then you see less
Yes,
Navier Stokes terms.
more narrow in velocity.
Yes. Do you see that in the simulations? You see that?
Yeah, I'll tell you.
I think you still see some.
No, he's saying if the distribution is becoming narrower,
Very just single velocity.
single velocity you won't see. But
But
yeah, you'll have.
Yeah, that's something. But just by making that narrower, you should just make that sharp and
yeah,
sharp.
no, yeah.
Yeah, okay.
Okay, so coming to your point, so this actually spreading is happening because of the initial conditions, fluctuations in the initial condition. Different realizations, you see that the shock position is a different position because at different realizations, the number of these rods, background rods that have entered here is different at till time t. And that fluctuates, and that fluctuations is coming from the initial condition fluctuations. So the number of rods that have entered in over a region from this and the fluctuation in that number should be proportional to the square root of the mean, because these are Poisson distribution, because initially I put them as independent particles. And one can find out this mean, and we can show that this mean is actually proportional to t, so it has a square root t scaling. Okay, so it's not very difficult to see, but this spreading doesn't happen indefinitely because we have a finite size system. So after some time, the spreading as well as the broadening both stops, and the spreading stops and the broadening stops. Here you can see that the density profile at 2 times I have just shifted because they are just moving. I have shifted to make them fall on top of each other, and you see that the spread as well as the breadth is same exactly at 2 times, 1000 and 2000 times. So it's not. So it's basically this thing. It goes there, starting from this width, and it goes there, and then keeps on moving like this. Okay. And the spread, the final spread that has the saturated spread actually is different if you have different system size, and it has a scaling as square root n, and that is also easy to understand because initially you had n order n number of background particles. Okay, But one interesting point to note is that such an initial condition never reaches a GG state, because I said that at the GG state, you should have a homogeneous time stationary state. But here you have a state which will keep on moving like this. So you do not have a time stationary state. It doesn't reach GG.
Yes, and that's the thing, I mean, so we say it will be forever, but I mean, if there is a variation in the density, I mean, there will be some spreading. Now, right? I mean, because the earlier scale is really just when the variation is in the limit of the variation is 0.
Yes. So that's why I'll make a comment. So you're saying that when you have a sharp change like discontinuities, then you will see this. If you do not have such, and to you have to be able to maintain such discontinuity. So that means you also need a singular velocity distribution. You have to start with, because otherwise you will not maintain that. I'll show you another example. Okay, so for this case, you can make some arguments, theoretical arguments, but it seems difficult to solve the full solve the Navier-Stokes equation. So you consider a simple initial condition, simpler initial condition for which one can solve the Navier-Stokes equation, which is you have uniformly filled gas and the velocity distribution is Maxwellian, but you have an additional particle of specified velocity V0 at the origin. And then this initial condition was studied by Lebois, Parkes, and Sykes, and they asked this question: what is the probability of finding the particle of this particular particle at position X at time t? So before answering this question for hard rods, let us look at for point particles. If the rods are point particles, then of course it will not see, because they become effectively non-interacting. So the distribution was initially delta function, it will just be a shifted delta function, right? Now, if you want to find out the solution from Euler GHD, so this particle, this component of the distribution has an effective velocity which is constant, because this is the background is already thermalized as uniform, and there is no velocity, average velocity. So it will not have any inhomogeneity into the effective velocity. So it is constant. So it should be again shifted, but now it's V effective times t. But if we do a simulation, we see a spreading. So this is your question. So this comes from the fluctuation from the initial conditions, because the number of particles process till time t depends on the how from the initial conditions, and that's why there will be a spreading. And in fact, this spreading has a probability scaling. So if you shift all these curves, already I have shifted. If you shift all these curves and then scale by square root, they collapse. And we find this function, scaling function, and it is Gaussian. And you can solve this equation and find this scaling function with explicit variance and the everything. And this actually solution was obtained by Lebois, Parkes, and Sykes, but they did it from a microscopic solution. But here you can actually solve this equation for this case, and you get this solution. Okay, but so from these two initial conditions, we see that neither of them actually reach GG, because even though this particle spreads, after some time it will stop spreading because of finite size, and then it will keep on moving like this.
So you imagine how anything in the ring.
No box, always in the box, because you can always map box to a ring for 2L length. So
the problem is there. That's why they put them alive. If you have an infinite system, it would eventually, I mean, would always spread, right?
But it will keep on spreading as square root t like this. So.
Yeah, don't bring it through. Eventually,
so whether you would call this as a thermalization or like this, it's just keep on spreading like Brownian particle is non-stationary. Right?
This is a finite volume effect.
And we see that if we for this we need a singular velocity distribution.
Yes.
Okay, so we wanted to see another initial condition for which and we see at least it will reach GG, and this is the third initial condition in which you have all the particles in the left half of the box, and their velocities are distributed Maxwell, and this is like free expansion experiment. So here you see that initially the density profile has a sharp change, but this actually doesn't remain like that because the velocities are distributed. And this is the evolution in the phase space. So this is how it evolves in phase space. Let's say this is X and this is V. So all the particles are in the left half, and it evolves like this. and at late time it produces these stripes in the phase space, which is similar to phase space evolution for non-interacting integrable systems, where you again see such stripes. So basically, you see fine structures. But if you look at the point particle but non-integrable case, where the masses are different, so the velocities mix, there you see that immediately where very short time it starts filling the phase space. So you see that it's already thermalizing to Gibbs state, but here it's not. These two are not. So if you look at the density profile evolution, initially it was like this sharp density profile, but later it did not maintain this sharp SOC. And because GHD, Euler GHD does not produce SOCs. And it actually becomes a nice, smooth function, and finally it goes to a homogeneous state. And also the velocity profile will go to completely zero, and everywhere it will be homogeneous, and the velocity distribution will be Maxwellian. And this is in this initial condition, it actually goes to GGE, and here we can actually compute. So once again, we map to the point particle, and the point particle problem in a box can be solved exactly. And then you come back, and once you come back, you get the complete solution of this equation. So you have this explicit expression, and you get the density profiles of the rods and the velocity profiles of the rods. Okay, so this is the okay, so this is the conclusion on the first part. So we have looked at different initial conditions and we saw that the solutions of Euler GHD can describe the evolution for genetic initial condition. However, there are some small discrepancies that arise due to Navier-Stokes terms. And to see the effect of this, you need to have fine-tuned initial conditions so that you have a sharp change in the density profile, and that remains with time. So, and such unless it is because the broadening is happening at a much larger scale, and spreading is happening at a very small scale. And if your your density profile is actually changing over a scale which is much larger than the spreading scale, you won't see the spreading. So that's why you need a very sharp thing. So which is also easy to understand that in the Navier-Stokes terms, if you remember, you had two derivative terms, del x, and you need such a sharp thing so that those contribution from the Navier-Stokes is very, very large. Okay, so now let me come to the second part. So before going into that, if you have any questions. Okay, so here now I will put these hard rods in a trap, and you can imagine that the integrability structure of the rods will be broken because the rods, the dynamics will not be integrable anymore, and there such broken integrability systems have been studied. One of the famous way of breaking integrability of non-interacting system is to add interaction. And in that direction, the famous problem is the Fermi-Pasta-Ulam-Singu problem. And there are a lot of interesting questions, like whether after putting a little bit amount of interaction, will the system thermalize, and what is the equilibration time scale, and lots of surprising results. This has a long history of more than 50-60 years. And the main points is that if the system doesn't thermalize for a very, 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 very long time, and the system has quasi-periodic trajectories and near perfect recurrences, no equipartitions, and so basically not very thermalizing situation. Another way of breaking integrability is to put an integrable system, let's say interacting integrable system, in an external trap. Okay, and you ask whether the system will be chaotic or ergodic. Will the system thermalize to usual Gibbs state? With the hydrodynamics, the usual hydrodynamics. Okay, so these are the questions that one can ask. In fact, the study of integrable system, trapped integral system, there has been started in quantum context. So this is a famous experiment in which this experiment actually considered motion of trapped one-dimensional Bose gas in a trapping potential, So they prepared initial condition in which they have a blob, but with one half has this momentum in this direction, another half in this direction, and they let them evolve. And they saw that these two blobs actually came, merged, and again went away and came, merged, and kept on oscillating like this. And even after 1,000 collisions, the system did not seem to thermalize such system. So the understanding of this extents had to wait till 2016, where these are the two papers in which this first paper from which this idea of generalized hydrodynamics came, and then there is an extension of this hydrodynamics in trap, which is called ballistic scale hydrodynamics, and which can explain many of the features of this experiment. So and also the predictions of this theory has also been verified experimentally in again cold atomic experiments. So two important points from these studies that I would like to mention is that the short-time dynamics of the trapped integral systems can be described by this ballistic scale generalized hydrodynamics. And at late times, the system does not reach a thermal Gibbs state. These are the two important points that came out from these studies. Now, question is, you should also expect such behaviors in classical systems also. And this was precisely asked by Zingu Kao, Birbal Chandani, and Joel Moore. They studied hard rods in harmonic trap. And let me summarize in one slide what they found. So they found that in the phase space distribution, this density actually exhibits finer and finer structure at late times. However, and the density, the small time evolution of the density can be described by the modified GSD. And this is what they say. This is basically, you have the trap, and this is the density at the trap. Let's say this is the density at the center of the trap. And they look at the evolution of this, and these points are from simulation, and this line is from the solution of this equation, and it matches perfectly. So that small time evolution is described by this hydrodynamic equation. However, they found that this system has Lyapunov exponent, which is positive. So it has chaotic, but it still can be described by kind of generalized hydrodynamic equations at small time. Second, although they said that at a fixed energy, if you increase number of rods, then this Lyapunov exponent decreases. That is understandable. And at very large time, the phase space density does not reach a thermal state, and it is described by the stationary solution of this equation. So these are the important points that they had said. We revisit this problem and we investigate these systems. So we not only we look at the small size systems and also the large size systems, and ask whether the system is ergodic. Can they support additional microscopic conservation law, like real conservation law in trap? Because you can see that the energy will be conserved anyway, and it is in external potential, momentum will not be conserved. But apart from that, will there be an extra conserved quantity? And do they thermalize in other? They looked at harmonic trap, but other we look at in aquatic trap also. And can chaos and non-ergodicity coexist in this system? So before going into the results, let me remind you, this is the Hamiltonian, and this is the trap potential. Delta equal to 2 is harmonic, and delta equal to 4 is aquatic trap. And these are the relevant parameters. So in this case, the energy, we have to consider energy scaled by, because the downstream energy is already of this order, n to the power delta plus 1 in this trap. So you should consider your energy to have a nice density profile, which is different from the ground state density profile. You should have an energy, excited state energy, which is of the same order of the ground state energy. So that's why this is a relevant parameter. And in quadratic trap, there is an extra conserved quantity, which is the center of mass energy. And apart from that, it seems that there is no other conserved quantity. At least it's not easy to figure out. So okay, so what we do, we perform molecular dynamics simulation. For this case, it's easy to do event-driven simulation, whereas here for the quadratic trap we do MD simulation. And we diagnose chaos, ergodicity, and thermalization in this system. Using the following probes, we look at maximum Lyapunov exponent, and then also look at the equipartition of energy. And for larger systems, we look at marginals of the distribution, like position and velocity distributions. Okay, so I have a slide for Lyapunov exponent, but I think all of you know. So maybe I'll skip this slide. So we look at, but one point I want to mention that if you have a chaotic system, this quantity that is defined, it will at later time, it will converge to a finite value. But if it doesn't, if it is not a chaotic system, suppose it grows as T power alpha, then this quantity at last time will decay as log T by T. Okay. So we compute this quantity for small number of hard rods. So let's say in quadratic trap, we look at 3 hard rods. And for different initial conditions, and for all these initial conditions, we find that this lambda t decreases, lambda t is defined here, it decreases as log T by T, which is usually a signature of integrable systems, because in integral systems, you see for Toda particles, you see that it has log T by T behavior. Whereas in quartic trap for n equal to 2, we see that there are many trajectories for which it actually saturates to some value. But there are other trajectories which still continue, till the time we have observed, it still continues to decay as log T by T. And it's not very clear whether it will saturate finally after some time. It's not very clear. So we see, and these initial conditions are chosen from microcanonical initial conditions with the given conserved values. For example, here is energy only, here is energy and center of mass value. And we have you can easily cook up a dynamics which will generate such initial conditions. So in this case, it's actually clearly looks like non-chaotic, but here you have both chaotic and regular type of behavior. And to see if this is ergodic, we look at the point color sections also. So for the quadratic trap, we look at the different trajectories, so the same values of the energy and the center of mass energy. We see nice regular point color sections, whereas here we see scattered maps, but it's not filling the full space. There are regions, pockets of these regions in which you don't see any such scattered points. If you start from here, actually you have regular trajectories. Wherever, if you start your initial condition here, you remain in this scattered region. So in this case, you see both types of trajectories, so this is so in this case, you see that the quartic trap for n equal to 2 is also non-ergodic. What about for n equal to 4? In this case, we look at again for different initial conditions, and you see that many trajectories have finite values of lambda at late time, but many trajectories still decay as log T by T. We look at the kinetic temperature, which is the running time average of the kinetic energy, and they also depend on initial condition very sensitively. So since they depend on the initial conditions, we look at the distributions, and we look at the distribution at different times. For example, we can look at the distribution of lambda at this time, and this time. And we see that at large n, the distribution actually converges to some stationary distribution at large t, at large time. And interestingly, you see that there was a peak at n equal to 4, and that peak actually goes as this peak at 0 means that these are integrable trajectories. There are some fraction of integral trajectories, and that actually goes to 0 at increase n, which possibly means that you had some non-chaotic islands in the phase space, which the volume of which it becomes negligible as the number of rods become larger. But at very large, and even though you see that the width of the distribution is finite, it's not a single lambda, it's still finite. So it possibly means that there is another conserved quantity which we don't know, and that's why it didn't take into account in the initial condition, and that's why it can give you a spread in the Lyapunov exponent, and consequently the distribution of the temperature is also wider, because that can depend on the another conserved quantity which we didn't take into account. Okay, so but the situation for quartic trap is not that. Here different initial conditions, they seem to converge to a given one unique value of lambda, and similar the temperature also, and you can see it from the distributions also. The distributions actually become narrower as square root t. As t increases, it becomes narrower as 1 over square root t, and also becomes sharper at some value. Okay, what about the average lambda? So here we see that the average lambda for the quadratic case is interestingly, it decays with increasing energy. Whereas for the quartic case, it increases to a square root e. Such a square root e behavior have also been observed in other thermalized systems, and I don't know whether it's it's very common or not, but it has been seen in other systems. But this is not kind of common, and this is not very difficult to understand, because as you increase energy, let's say you have a number of rods and you increase energy, huge energy, so they can explode and climb against the harmonic well and explore larger region, and effectively they become like point particles. So as you increase more and more energy on the scale over which they can explore, with respect to that, they becomes like point particles. And the point particles become, it's basically with increasing energy, this model goes to the integrable system. So that's why lambda is decreasing. It's consistent. Okay. So now,
But then why does it decrease with the particle?
sorry?
Why does it increase with the particle?
No, but in the aquatic trap, probably it doesn't explore that much because it's much deeper. It still explores. Yeah, but this argument doesn't work. Okay, so then we look at if the larger systems thermalize, and for that we look at let's say initial condition which is similar to the Newton-Scatterall experiment. We look at two blobs. We consider two blobs of densities which are separated in space. So this is the initial condition, this dashed line, and the velocity distribution is Maxwell, which is in this dashed line, and then we let it evolve. We see that the distribution from this, it actually converges to this distribution, which is different from, this is the Monte Carlo distribution that you get from, this is the thermal distribution that you get from Monte Carlo simulation. So it goes to a stationary state as far as the data goes, but it is different from the thermal state. So the stationary state, even in the trap, is different from the thermal state, and for the velocity distribution also. Okay.
But yeah, so there you have another exact quantity center of mass, right? So you have to put it.
I mean, till now we don't know. We couldn't find it. So it looks. So this is also is consistent with the fact that there could be another conserved quantity. If we take that another conserved quantity and then do the Monte Carlo, it could be that, but we don't know what is the conserved quantity.
But you were the center of mass.
No, center of mass we took it.
You took that into account.
Yeah. So energy, center of mass, and there is an extra that we don't know. So.
Sorry, in this expression there, so the graph you have there, so the initial condition is very close to thermal. Is that right?
For the velocity, yes. But still,
it's not quite.
yeah, but still it goes to this distribution.
It goes something very different. I see a long times, but it's you start with what do you start off with?
This is actual distribution.
Okay, so you start out with a macro distribution.
Yeah,
so it should be thermal. It should be the same. Is it? I don't
No,
know.
no, but in rods, in trap, it cannot be.
Okay, yeah, of course.
In trap, it can.
Okay, fine. So it's you're missing out the effect of the trap.
Yes.
Okay.
So then, so that's why initial and the Monte Carlo thermal is very close, but it actually settles here.
It goes away. I can see that. It goes
Yeah. And this you can also measure from this distance between rho and thermal distribution, and you can see that. But what about aquatic trap? And we do the same thing. In aquatic trap also we look at two blobs initially in the space, so two separated density blobs, and the initial distribution, velocity distribution is Maxwell. And you look at the evolution, and finally it actually goes to the Monte Carlo distribution, both in the density as well as in the velocity. So initially it was Maxwell, then it goes out of the Maxwell and comes back to the Maxwell again. Yeah, so here it actually thermalizes for aquatic trap, it thermalizes. Okay, so since in quadratic trap it doesn't thermalize, so it doesn't match with the other initial, the stationary distributions doesn't match with the thermal distribution. So we wanted to see, is it unique? Will it depend on initial condition? And we looked at these 4 choices of initial condition, 4 types of initial conditions, and we see that for different initial conditions, all of the stationary distributions are different, and none of them are matching with the thermal distribution. And for both cases, and which once again kind of can suggest that there could be an extra conserved quantity.
Okay, yes,
Yeah.
How many parameters describe the final distribution? How many extra quantity would you have?
That we don't know.
You can measure that.
Yeah, I don't know. Maybe we should discuss. We do not have any good method. Yeah.
You can evaluate, some set of observables, whatever they are, choice, and see what kind of submanifold it goes, what the dimension of the submanifold it goes per time.
I see.
Then you should get the number of quantity.
I see. Yeah, maybe we should discuss it. Yeah. So.
Potential like x to the power delta, right? That's what we're taking. Because the delta equal to 2 is a special case where it's stronger. So
Yes.
is that the correct statement?
Yeah, so it looks like that there is, so you would imagine that only energy would remain conserved. And at delta equal to 2, you see that the center of mass energy is also conserved. But apart from that, it looks like there is an extra conserved quantity.
But is it true only on delta equal to 2 or delta less than, what are for delta less than 2?
Delta less than 2, we didn't try. I think for delta equal to 1 also there will be similar thing. I think, yeah, I think, but
Delta equals 1, there will be also.
yeah, I think, but I think, but I didn't check. I should check.
To me, delta 2 is probably special because the energy is that square, right? The daily and special relation.
I see. No, for delta equal to 1, why I say that the dynamics, you can see that in the dynamics, you can actually map to point particles again, except at the equations. So it's very close to the point particle dynamics, extremely close to. So in that sense, I was thinking that maybe there could be.
Yeah.
Okay, so this brings to the last slide of my talk. So let me not go through completely. So first of all, if you ask these questions and these are the answers. So, and these answers is consistent with this possibility that there is one more extra conserved quantity which you don't know. But then this paper says that at small time the dynamics is very well described by ballistical GHD, which is if there is an extra conserved quantity, it could be just the hydrodynamics with these 3 conserved quantities. But here it says that at small time it is given by GHD. Maybe at very small time they behave like integrable particles, so it could be. So, and we may expect that maybe there is a crossover from GHD to normal HD with time. But interesting fact is they say that at intermediate time, this macroscopic evolution do not follow this GHD equation. However, the stationary state is described by the stationary solution of this. So then it's very, I don't know how to reconcile all these facts. So that's why these are the kind of questions that we want to explore in the future. So this, yeah, this is the last slide. These are the references. So thank you.